Hey everyone, and welcome to The Explainer. Today, we are going to go on a bit of a mathematical adventure. We're going to kick things off with a question that sounds almost, well, silly. And by the end, we'll have uncovered the entire secret life story of a pretty complex mathematical creature. So, let's get our detective hats on and start the investigation.
Okay, let's start with something we can all agree on. Solid ground. 2 times 2 is 4. You probably learned that before you could even tie your shoes. We can also think of this as 2 raised to the power of 2. Multiplying a number by itself a whole number of times? Yeah, we can all picture that, no problem. But what about this, 2 to the power of pi? I mean, think about it. How in the world do you multiply something by itself 3.14159 times? You can't just do it 3 times and then a little bit more. It just doesn't make sense. It feels impossible, right? Well, this little puzzle right here is actually the key that unlocks a much, much deeper way of thinking about the world. So yeah, that's the big puzzle. Powers with whole numbers are easy. Even fractional powers, like 2 to the power of 1/2, that's just the square root of 2. We've got rules for that. But these irrational numbers like pi, man, they break all the simple rules. They just go on forever, no pattern, no end in sight. So how do you even begin to deal with that? Well, one of the classic ways is to sort of trap it. We know pi is somewhere between 3.14 and 3.15. So it stands to reason that 2 to the power of pi has to be somewhere between 2 to the 3.14 and 2 to the 3.15. And we can actually calculate those two because those powers are just fractions deep down. Then, we can squeeze the boundaries tighter, 3.141 and 3.142, and so on, getting closer and closer forever. It's clever for sure, but it doesn't really feel like a true answer, does it? Exactly. You can just feel the collective sigh of mathematicians everywhere. This squeezing method, it works technically, but it's just so unsatisfying. It's like trying to describe a beautiful painting by only listing the colors it doesn't use. It just lacks elegance. It feels like we're missing some fundamental language for how things grow. And as it turns out, we are. And that secret language, that better way, is built around one single special number. It's a number that's just as fundamental to our universe as pi is, but instead of circles, it's all about growth. So let's meet the real star of our show today, the number e. So just like pi, e is an irrational number. It goes on forever, never repeating. And you find it popping up everywhere in nature. It's in the way a colony of bacteria grows, the way your money earns compound interest, even in the way a simple chain hangs between 2 posts. It's like it's woven into the fabric of the universe. It's nature's number. Now, when we use e as the base for a power, we get what's called the exponential function. And look, you can forget that scary-looking formula for a minute. The best way to get a feel for e to the x is to just imagine something growing, but its growth is instantly and continuously added back into itself to create more growth. It's like perfect, seamless, 100% compounding. That smooth, natural process is the exponential function. And this is the whole reason e is so incredibly special. This is its superpower. The speed at which e to the x grows is exactly equal to its current size. So when its value is 100, it's growing at a rate of 100. When it hits 500, it's growing at a rate of 500. This self-referential growth is what makes it the absolute perfect, natural way to describe any system that builds upon itself. Okay, so now we have it. We have our elegant tool. With e and its perfectly natural growth function in our back pocket, we can finally go back to that original 2 to the pi puzzle and solve it in a much, much more satisfying way. And here it is. This is the big aha moment. It turns out that any exponential expression, including our pesky 2 to the pi, can be translated into this universal language of e. So 2 to the power of pi is just e raised to the power of, well, the natural log of 2 times pi. Don't let natural logs scare you. All it really means is, how long do you have to let e grow to reach the number 2? That's it. And since we have this one beautiful single definition for e to the x that works for any input, it now works for everything. Integers, fractions, and yep, even our irrational numbers. Problem solved. Beautifully. And you know what the best part is? This powerful new way of seeing things doesn't break any of the old exponent rules you spent all that time learning in algebra. Not a single one. They all still work perfectly. So this new definition is a true upgrade. It gives us all this new power without taking anything away. So, what's the big deal? Why does all this matter? Well, because with this universal language for growth, we now have a solid foundation to understand change. And that's really the heart of calculus. This lets us become mathematical detectives. We can take pretty much any function, no matter how gnarly it looks, and we can uncover its entire life story.
And every good detective has a checklist, right? To investigate a function, we just ask a series of questions. First, where does it even live? Where does it cross the main roads? Does it have any invisible fences it can't get past? Where are its highest and lowest points? And finally, how does it bend and curve along its path? All right, let's open up our case file. Okay, here is our suspect. Now, I know, it looks a little intimidating, but armed with our detective checklist and the tools of calculus we just unlocked, we can systematically break this thing down and understand everything about it. We are going to build a complete profile of this function. So, the investigation begins. We're going to walk through our checklist, step by step. And with every clue we uncover, the picture of what this function actually looks like is going to get clearer and clearer until its entire story is right there in front of us. All right, clue number 1, the basic profile. We start with its domain, which is just a fancy way of asking, where does this function actually exist? Turns out it's defined for all real numbers, so its story has no mysterious gaps. Next, symmetry. Is it a perfect mirror image of itself anywhere? Nope. And finally, continuity. Can we draw its graph without ever lifting our pen from the paper? Yes, we can. So we know our suspect's path is totally unbroken. A great start. Next up, let's pin down some key landmarks on our map, the intercepts. This is just where our function's path crosses those mean horizontal and vertical axes. So we find it crosses the vertical y-axis at about 1.587. But even more important, we see that it hits the horizontal x-axis, that's where its value is 0, in exactly 2 places, at -4 and a +1. These are like giant push pins holding our graph down. So what about its behavior way out at the edges of the map? Does it have any invisible walls it can't cross? These are called asymptotes, and we find it has no vertical walls at all. But as x gets really, really big, positive or negative, we find something super interesting. The function's path gets closer and closer to a perfectly straight, slanted line, an oblique asymptote. Just think of it like an invisible guide rail in the sky that the function follows as it flies off towards infinity. Now for the exciting part. Every journey has peaks and valleys, and a function's path is no different. We need to find its turning points. By using our tools to find where the path flattens out, just for an instant, we discover 2 critical spots. There's a local peak, a little hilltop, at x equals -7/3, and there's a local valley, right at one of our anchor points, x equals 1. Now we're really starting to see the shape of the landscape. Okay, the final piece of the profile. How does the path itself curve? This is called concavity. Our investigation shows that way out to the left of -4, the curve opens upward, kind of like a smile. But after that point, it flips over and starts to open downward, like a frown. And that exact spot where it changes its mind, right there at x equals -4, that's an inflection point. It's a moment where the whole personality of the curve just transforms. And just like that, there you have it. We started by pulling on this one little thread, a simple question about a power that seemed impossible. And it led us to E, the universal language of growth, which then gave us the tools to become mathematical detectives, capable of writing a complete biography for a function that, at first glance, seemed totally unknowable. And that really leaves us with one final thought. This whole process, it's not just about some abstract squiggles on a graph. It's a blueprint for understanding complex systems. So it makes you wonder, doesn't it? What other systems out there, in biology, in finance, in technology, are just like this function? They look impossibly complex on the surface, but they're just waiting for the right detective to come along with the right tools and reveal their secret story. Thanks for joining the investigation.